In this example, we want to describe the behavior of the following sequences. So we want to determine if they're monotonic, if they're bounded, and whether they converge or diverge. Okay, so let's look at this first one. I'm just going to write out the first few terms because I think it's illustrative of what's happening here. So a sub n is 1 over n. So that would be, if we wrote down the sequence for a sub n, it would be 1, a half, a third, a fourth, a fifth, and so on. No, the problem did not specifically ask for it. It's just, kind of looking at it just to kind of get a visual sense of what this sequence would be like. All right, now the end behavior of this we can determine pretty easily. I mean, we can take the limit as n goes to infinity of a sub n, which is the limit as n goes to infinity of 1 over n, which would be 0, right? Interesting. Okay, and you can kind of see, yes, of course, this is getting smaller and smaller and smaller. It'll never be negative, so it's just getting closer and closer to 0. Now, let's answer some questions. Is it monotonic? Yes, right? It is definitely decreasing. And decreasing is a form of monotonic, right? It doesn't go up and then go back down. Is it bounded? Yes, right? It's bounded by 0. Right? Again, the downward direction, so we're interested in where it's bounded on the lower end. Technically, it never gets higher than 1, but that's irrelevant, right? That's not really important. What it's important is, since it's decreasing, is it bounded on the low side? And it is. Is it convergent? I guess I could say convergent or converges. And the answer is yes, right? It's converging to 0. Right? It's bounded and monotonic. So it's definitely converging. So once it's bounded and monotonic, once these two are yes, then this one's definitely a yes. And it's converging to 0. Let's consider a Desmos graph just to kind of verify what we're doing here. So you can see that I have this table. There's a table there, I promise. And then you can see those values and they're shrinking, right? So if I let x get larger, get larger and larger and larger, you can see that that sequence is shrinking, right? Getting smaller and smaller and smaller. So it is indeed bounded. It is monotonic. Wonderful. All right, let's look at letter B. Letter B is n squared divided by n plus 1. So if we look at those values, b sub n would be equal to, all right, so if I put 1 in, that's 1 over 2, so that's a half. If I put 2 in, that's 4 over 3. 3 in would be 9 over 4. 5 in would be, 4 in, sorry, 3 in, 4 in. 16 over 5, and then 25 over 6, and so on. Well, that's a little hard to kind of spot what's going on, so let's use Desmos, because I don't know if you can all see it with that. So let me use Desmos, because Desmos will, of course, have decimals. See what's going on? The number's getting larger and larger and larger. So it's increasing, right? I can get more values. By the way, if you've put in the first couple, like 1, 2, 3, it knows you want to increase by 1. So then you can just press enter, 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 and it'll just keep making them, which is nice. All right, so we can see that this is getting larger and larger and larger. And so therefore, it's monotonic, but it's not bounded. So we will say monotonic. Yes, right? It is definitely increasing. And of course, if you wanted to, you could put the decimals here, right? So this would be 0.5, 1.3 repeating, 2.25, I think it was, and then 3.2, and then 4.16, and it was just going on and on and on, right? All right, so then bounded was a big no, right? So it's not bounded above, and that's the important part. because it's increasing, we want it to be bounded above. Which means it is not convergent. As a matter of fact, we can tell it's diverging to infinity because of the increasing without bound. It's just growing and growing and growing and growing and growing, right? So if I put, I don't know, 100 in here, there you go. But if I put 1,000 in here, right? If I put 1,200, just so you don't think it has to be going to 1,000, it's not. It's just growing and growing and growing. All right, so that's letter B. Letter C is so obvious I don't really need Desmos for it, but I can show you Desmos if you're interested. So this one is -1 to the n. So -1 to the 1 would be -1. Then 1 squared would be 1. Then -1, then 1, then -1, then 1. And that is not monotonic. That's a big no to the monotonic. And it is not convergent, you can tell. It is bounded, however. It's bounded both above and below. So this would be yes, because it never gets above 1. So it's bounded above by 1. It's bounded below by -1. However, just being bounded is not enough to make it convergent. So it actually is divergent. It's divergent because it's not monotonic. It's just hopping around. It's not diverging to infinity, right? It just never gets anywhere in particular, right? Just bouncing between 1 and -1. All right, now what about D? So what if I have it so that I am letting -5 raised to the n power? Well, that's the same thing, by the way, as -1 to the n times 5 to the n. They are one and the same, right? Okay, so how would that look? Well, if I put in 1, it would be -5. But if I put in 2, it's +25. If I put in 3, it's -125, and so on and so on. I think the next one's 625. That's not monotonic because it's bouncing, and it's not bounded either because it's getting larger and larger, both in the positive direction and the negative direction. I can show this to you in Desmos if you want to see more values. So there was 5b, so we're done with that. There's C in case you're interested. It's just 1, -1, 1, -1, so it's kind of boring. And then D, yeah, look at those numbers. So it's just getting bigger and bigger and bigger, right? So that's going to -infinity for the odd numbers and +infinity for the even numbers. So therefore, it is not monotonic. It is not bounded. It is not convergent. Now, it's not actually diverging to infinity. It's diverging to both positive infinity for evens and -infinity for odds, which means it's just a straight up no. It's divergent. If you wanted to look at only the positive numbers, let me just make a little note to you, because this will come in handy for us several times in chapter 10 and 11. So if you want to make it so that it's only positive numbers, only positive powers, I don't know why you would do this with a -1, but it would be -1 to the 2n. That will only be positive numbers. Or say, for example, -5 to the 2n. That would work. If you want only negative terms, there's a couple ways to do that. 2n, by the way, is always positive, right? 2, 4, 6, 8, 10. So if you only want negative powers, it'd be -1 to the 2n plus 1, or say -5 to the 2n plus 1, or you could do -1 to the 2n minus 1. That's also always odd, right? So these are even powers. I guess I should say only even powers. Let me do it that way. These will be only even. They're working out to be positive just because it's an alternating sequence, but I'm really more interested in the even and odd thing. Sometimes that gets missed in pre-calc and you don't realize it. So to make it so it's always even, you use something like 2n. 2n is always even, or 4n, or something like that. If you want odd, you either do 2n plus 1, or you do 2n minus 1. Now, there are other ways as well. 2n plus 3 would work, or 2n minus 1 works. I mean, there are other options, but these are the most common ones, right? So 2n plus 3 would always be odd, etc. So you better make a note of that, because we'll need that on a semi-regular basis. We'll need to work with only evens or odds. So that's how to make evens and odd sequences happen. So you work with 2n minus 1. 2n plus 1 is most common. Sometimes 2n minus 1. You can do 2n plus 3, 2n plus 5, 2n plus 7. Those all work. There are other options, but these are the most common ones. And I can prove it to you with Desmos. So there was negative 5 to the 4n. Isn't that lovely? And then I'll just make a little folder here that's illustrating even powers so you can see. So if I want to make this n5, for example, and then let's keep with the negative 5 just for fun. So negative 5 to the 2n5. And so if I put in 1, 2, 3, not 34, 3, 4, and I can just press enter. It knows what I want to do. Now notice, let me go back to this one. Which ones are getting picked up? The 2, the 4, the 6, right? 6 right here is 1, 5, 6, 2, 5, and that's 3 down here, right? So it's picking up only the positive values, but what it's really picking up is only the even powers. Now if I do the same thing with an odd combination, so let me make another folder. And hold on. I guess I'll make this even and odd. I can keep it in the same thing. Okay, so for an odd power, if I do n6 right here, and then I say negative 5, but I want to do 2n6 plus 1, right? Plus 1's the most common one. Oh, that's right. So in Desmos, it doesn't like me adding that after the fact as a power, so I'll have to put parentheses around my power here. It generally doesn't like working in powers unless you tell it to. So then if I say 1, 2, 3, 4, and so on, notice which numbers it's picking up. The negative 125, the negative 3125. What it's picking up is the odd powers. So it's getting the 1, the 3, the 5, and so on, right? So 2n plus 1 picks up those odd powers, right? So even and odd, 2n or 2n plus 1. And that's a topic that we will use repeatedly. That's a little trick that we'll use on a regular basis. So it's technically an arithmetic trick, or a powers trick. It's really more arithmetic because it doesn't have to be powers. I take it back. You can do it all sorts of things. So this is just an even odd trick. You should have seen it in pre-calc, but just in case you did not, there's how to do it. And I'll put a little highlight box around it just in case we need to refer to it later, which we will. We definitely will.